So let's talk about tone and harmonics. The last part of this, when you're filling it out, this is where you have a lot of information about tones. And if I get to, there's a slide, there we go. Every sound has its own, what we call the quality of the sound. It's the tone. We can differentiate between a flute. I meant to say flute, and I was going to say piano next, and if you take piano and flute and put them together, you get a flute. Anyhow, we can differentiate between a flute and a piano playing the same note. Even if they're the same frequency, same pitch, same loudness, we can still say, oh, that's a flute, and that one over there is a piano. And the reason we can do that is because of the quality of the sound, the tone of the sound. And tone, it's really hard to describe. What you're really getting into is what we call a fundamental frequency or a fundamental pitch. And that fundamental frequency or it's called the natural pitch or the natural frequency. And almost everything has that, a natural frequency that it wants to vibrate at. If something's vibrating at its natural frequency, we call that the first harmonic. So what I have here is I have a violin, and the violin right now has all kinds of different things going on with harmonics. But the most natural frequency that it can vibrate at is the first harmonic. And the first harmonic, so this is supposed to be set up like in this string right here. The first harmonic, I'm going to make it go a little faster, would look like this. This is the natural frequency of that string. But everything can have more than one tone, more than one harmonic happening to it. And if we have more than one, the other things are called overtones. But this is the pleasing sound. This is the sound. The other overtones are what give it its unique quality. So what we have now is we have the first harmonic and the second harmonic going at the same time. And when they're going at the same time, those two waves are going to either constructively interfere with each other or destructively interfere. And we get the interference that happens as a result. So here's the, I'm just going to play the second harmonic so you can see that. I'm going to play the third harmonic so you can see that. And basically what we're doing is when we're going from the first to the second to the third, is it's still a natural frequency. We're putting multiple units of waves in here. Like if you can see, this is 1.5 waves. If I go to the fourth harmonic, that's going to be 2 full waves. If I go to the fifth harmonic, that's going to be 2.5 waves. And there's almost like a little bit of a math formula that we're starting to develop as we go through these. So another example of frequency or natural frequency is this tuning fork. I'm going to go full screen here for just a moment so that you can see my tuning fork. There it is. And I've had this, I showed this to you once before, tuning fork. If you strike the tuning fork, it's vibrating at its natural frequency right now. And every time you hit it, it's the exact same tone, it's the exact same quality of sound. We're probably hearing only the first harmonic in this case, and not any overtones. What happens with something like this, since it's on top of this box, is we get what we call forced vibration. So not only is the tuning fork vibrating at this frequency, but it's actually making the entire wooden box vibrate at the exact same frequency. And forced vibration happens if you can get a couple of things that have the same natural frequency so that you can hear them better. It's called forced vibration. And forced vibration, like for example, if you take a tuning fork and I put it on a table, I could make the whole table vibrate, and it's going to almost like amplify the sound. What we're doing is we're getting those waves set up in the table, and we're getting the waves set up in the tuning fork, and there's so many waves going back and forth that they almost like create a standing wave. If I can get a standing wave set up in something, because of the nodes and antinodes, the sound almost tends to get like super amplified. I'm going to show you another natural frequency of an object right over here. I got it set up, that little disc up there. I don't know if you can see that. I'll go full screen here for just a second. And I got myself this bow for playing like a violin. And if I just rub it at first, it'll be very quiet. But I'm going to create a standing wave in the disc. So what you heard was the natural frequency of that disc right up there. I'm going to put a different disc on there. I'm going to show you both of them side by side here in just 1 second. So this is the one that I just used, and you heard its natural frequency. Here's the one that I'm going to use. And you can see the difference. This one right here is much smaller. So I kind of want you to right now predict, like, what do you think the natural frequency is going to be in terms of its frequency? Is it going to be a higher pitch or is it going to be a lower pitch based on what you learned about sound so far? So I got that one set up and we are ready to go. I got to turn my computer here. There you go. There's the disc. Here's my bow, same bow. Is it going to be a higher frequency, higher natural frequency, or is it going to be a lower natural frequency? Like I said, when you first start to play the sound, it's very quiet at first, but then as you continue to move the bowstring across the bow, you get that standing wave set up and it amplifies upon itself. We can do some really cool things with this idea, because what I'm getting into now is something actually called resonance. And resonance is super cool. It's when you force the vibration in an object and the standing wave sets up, and when the standing wave sets up, there's amplification as a result of it. The greatest example of this that every physics teacher in the world is always going to show all of their students, probably from now until the end of time, is the Tacoma Bridge example, where they built this bridge. Here we go. Get the video playing for you. It was a long time ago, 1940. They were building this bridge, and what happened was they didn't take into account the fact that there was wind that was going to be blowing through this channel. So obviously the bridge is going over water, because that's why you would build a bridge in most cases. And I'm going to get to the point to where the bridge is built, and it's passing over this water. And here you go. Here's the opening day, and it's beautiful. And there's American flags, and there's the bridge. And they didn't account for the wind. And apparently, when the wind was blowing across these cables, they were hitting the cables. That the cables were cut just right, so that they were at standard wavelengths for waves that could be set up in them. And what we've learned is now when we cut people do the math and they say, well, we don't want a wave set up in this cable, so they make it not a standard wavelength length. But in other words, basically what happened was a wave was set up in the cable, and the wave continued to set up upon itself, so it created a standing wave in the cable, and then that caused the one next to it to create a standing wave, and the one next to that. And eventually what you get is, this is steel and concrete, you guys. And you get a standing wave set up in this bridge that's steel and concrete. It's absolutely amazing that a bridge, so here's the pictures of the wind that are blowing through the channel. It's absolutely amazing that steel and concrete and cables can move like that. And if you look, it looks just like a standing wave. You know, the wave doesn't look like it's traveling to the left. It just looks like it's going up and down and up and down. And that's like a 3-foot piece of concrete moving like that. Absolutely amazing that natural resonance or natural frequencies and resonance can do that. Here's another great example of it where, there's people that do the wine glass kind of thing, and you've probably seen this. You can take a wine glass, take a little vinegar, and rub your finger on the rim of the wine glass.
Thanks for joining us at 7:07. We're going back to the lab for more physics fun.
Wise guy Matt Sullivan is joining us live from his lab this morning, and today he's breaking glass using nothing but sound. Good morning, Matt.
Good morning, Robert. Hi, Gay.
How are you today?
I'm just great. Now, at the end of the last thing we did last week is I played around with a wine glass, you might recall, and I showed this phenomenon of resonance.
I remember because I couldn't do it.
Right, right. It takes just a very, very highly trained finger, just like this. I'm just kidding. And so we hear this nice loud sound that I'm just barely touching this glass. And the question I asked was, if I pour some water in here now, is the pitch of that sound going to get higher or is it going to get lower? And the correct answer was sent to me by Tiffany Hubbard of Tuscola, who's a 7th grader there, who thought about her musical instruments and figured this out. And she knew that it gets lower. So when I do this now, you can hear that you have a lower pitch. And the reason for this is that the frequency that something vibrates at has to do with a couple of things. How springy it is, and the springiness doesn't change by putting water in there, and also by how much inertia it has. And the water has the effect of increasing sort of the inertia of this cup, and so the pitch goes down. and you can see the water waves in there. You can play around with this at home. It's very cool. But the point here is that an object likes to vibrate at a certain frequency, and wine glasses have very specific and sharp frequencies that they like to vibrate at. And so I have over here a wine glass that I have set on this little tray. Right next to it is a speaker, and if I turn on this annoying sound generator and I put sound into the speaker at the exact same frequency, you're going to see that the glass starts to vibrate because that little piece of tape that's sitting on top is going to move.
Very good.
Okay, now it actually vibrates quite a lot. You can't see it unless I do this. I have a strobe light, and now I'm putting the strobe light on here, and this strobe light is going at about the same frequency as the speaker is, and as the glass vibrates. And when I turn it up, can you see the top of that glass kind of oscillating, sort of breathing? It kind of goes like this. If you look at the opening of the glass, it has that kind of a motion.
I can't see what he's talking about. I don't
Could
know.
you see that?
Maybe
Yeah.
you can.
Okay, so what I'm going to do now is I'm going to turn the speaker up louder. That motion is going to get larger, and so we're putting more and more energy in at this one frequency. The amplitude of the motion gets bigger and bigger and bigger. It's like pushing a kid on a swing. If you keep pushing, eventually you can go right over the bar. Okay, so we're going to keep pushing by putting more and more loud sound into this glass, and eventually the oscillations are going to get so large that the glass is going to break. So let's just do that. Right? I better put on my purple glasses. It's very scientific piece of safety equipment here. Okay, so here we go.
Oh,
I love that. Okay, so it's not every week we get to break something, but, you know, it's a special week when we do.
that is true. Okay.
So it's kind of a neat video showing how resonance can build up. It's basically the same thing that happened in the bridge. The standing wave set up so much that the structure couldn't handle anymore. The bridge actually did collapse. I didn't actually let it play till that happened. This is just neat that somebody can do this with the wine glass, natural frequency resonance kind of a thing. It's just a great example. Sorry for the quality of the video is really bad, but so very cool that a street performer can do that. So the last example of resonance that I want to show you is something called Chladni patterns. I've heard this pronounced a bunch of different ways. I've heard Chladni patterns, Chladni patterns, Chladni patterns. I've looked it up on the internet and you get all the different pronunciations. It's named after a particular person, but basically it's kind of like with instruments, particularly violins and guitars and those types of things, that the bass of the guitar is made in such a way that standing waves will set up in the bass, and that's part of what gives the guitar its unique sound, and also helps the bass of the guitar or violin or instrument amplify the sound that's coming out when you're playing specific notes. So what I did for this was I set up this disc over here. So you can see I got this disc set up on the table, and underneath it is a speaker, and the speaker is set up to my wave generator. And all I'm going to do is change the frequency. And you'll hear what happens when I get to one of these areas of a standing wave being set up. I'm only changing the frequency. So I'm only changing the frequency that you can hear what a difference in sound it has, but it's really cool if I actually do something else. And the really cool part comes when I put my camera up there and aim it down at it and sprinkle a little sand on that plate. So give me just a second to set that up. Alright, so I got my camera up above it. I got some sand that I sprinkled on the plate. There we go. And all I'm going to do is turn it on. And when I turn it on, you're going to see these areas of standing waves. And this is going to be a refresher course on what standing waves look like. So right now you can't see it from the aerial view, but these little sand things are bouncing up and down. Here we go. Let's get to that standing wave. So, super cool. Apparently my plate's not perfectly level because some of the sand was moving that way, but really super cool. This is a place where there was no vibration, vibration, no vibration, vibration. So we had a series of nodes and antinodes set up in the plate, and when you get that standing wave set up, super amplified sound. Let's try to find another one. Close to one right there. I'm going to actually move way down in the frequencies. And you can see them vibrating around now. So that's just regular waves in the plate. Let me change the plate. So I obviously put a square plate on there now, and we can make some standing waves in this as well. Felt like there's one right in there. There we go. Oh, that is super cool. All I'm doing is changing the frequency. Here comes another one. So cool. All right, so the last topic that I have for you is something called beats. No, they're not the headphones. This is what happens when you have sound interference. So I'm once again going to demonstrate that with the oscilloscope, and I have a couple of ways, a couple of things that I'm going to show you with that. And then I'll show you how we can do a little bit of a math calculation to determine what the beat frequency is. So first thing I got to do is I got to set it up, and then I'm going to show you kind of the setup, and then we'll listen for some beats. Alright, so what I have is I have a wave generator over here on the right, the oscilloscope in the middle, showing both waves at the same time, and a wave generator over here on the left, which is how I'm going to make the beats, because you have to have two different frequencies to make beats. There's speakers on top of both wave generators. There's one speaker there, there's one speaker there. I'm going to leave that one alone, but right now what I want to focus on is the oscilloscope. If you can see the two waves on the screen, you would see that they're both perfectly in line. Man, when I look at the screen right now, it looks like there's only one wave, but there indeed is two. So let me just flip a couple switches here. I'm going to flip this so that it's showing both at the same time. And what we see is that those waves are perfectly in line. And that open circle works just like that. By the way, if a speaker isn't playing anything anymore, I can use this speaker as if it's a microphone. All a microphone is in a speaker. They're just the same thing. They're in reverse. So if I put this up to my face and go, you can hear my voice on the screen. And I'm trying to match the sound of that perfectly. I'm just going to turn the speaker back on though, because I have a machine that'll match it, and you can see what happens when the machine matches it. Perfect circle. If I change the frequency of one of them, so I'm going to get it so you can see both the generator. There we go. Let's change the frequency. Change the frequency more. And you can see what's happening on the screen when that happens. But more importantly, I want you to hear what it sounds like. So there we go. They're both the same right now. 391, 391. Well, let's get this one up to 392. There we go. Get that perfect circle on the screen. Hear that? Sounds like one tone. Hopefully the microphone is good enough to pick this up. I'm just a little off and it's going woo, 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 woo. Back to one tone. Woo, 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 woo. That's what we refer to as a beat when it makes that sound. So let's get out of the big cam mode. Different a math formula. It just simply says that if you want to know what the beat frequency is, you take the frequency number 1 and subtract from it frequency number 2, and you have the beat frequency. So for example, what's the beat frequency between the following two frequencies? If one of them is 440 and one of them is 448, you subtract the two numbers, the beat frequency would be 8 hertz. That's it. Easiest formula of the year, and it's the last one we're going to do. 8 hertz is the beat frequency. By the way, this is kind of how people like tune a piano. They have a wave generator like what I have, and it plays one frequency, and then they tune the string until they no longer hear the beat frequency. And when you no longer hear the oscillate and the woo sound, that's when you know you've tuned the piano properly. Here's another example. The piano tuner hears a beat frequency of 4 hertz. So he hears it going woo, 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 woo. And he knows it's supposed to be tuned to 320. Well, if he's hearing a beat frequency of 4 hertz, that means that the string of the piano is either at 316 or 324. One or the other. Don't know which way it would have to go. I'd have to start to tune it and try to get it closer, but I know that the beat frequency is either going to be 316, or I'm sorry, the piano string frequency is either 316 or 324. So that's it for the Edpuzzle notes on sound. You're going to have an assignment where you're going to have to do some of the beat frequencies, and we'll get that worked in. So for now, see you later.